Hey there, Andy Staines. How you doing, guys? So I'm just wanting to talk to you a little bit about atomic structure and how that works alongside electron flow. What that means in terms of circuits. How these two things come together to make current flow in a circuit. So we need to start somewhere, and probably the best place to start is looking at what an atom is. Now, atoms are the smallest bit that you can divide material down into. Some materials are made of molecules which are one or more atoms of one or more different type joined together, but those can be broken down into individual atoms. So an atom is conventionally seen as a nucleus surrounded by a shell, number of orbits of electrons. Okay, so it's kind of quite a simple principle. Now, within that atom, within the nucleus, which is in the center, we have got a number of subatomic particles. So I'm just drawing here in the red protons. We also have within our nucleus some neutrons, drawn in pink. And so those go together to make up our nucleus. Okay, so the nucleus consists of protons and neutrons. Orbiting around our protons and neutrons at quite a considerable distance, we have a cloud or shell or layer of one or more electrons. Okay, so the electrons orbit around the nucleus. Now, we're talking about electricity here, so we are needing to talk about how an atom behaves with electricity, how it behaves electrically. And it's very simple. We have charges. Now the components, some of the subatomic particles in the atom are charge carriers, have electrical charges. The proton has a positive charge, a plus charge, and the electron has a negative charge, a minus charge. So overall, the nucleus is positively charged and our electrons are negatively charged. Now the neutrons have zero charge, so there's no charge on a neutron at all. Okay, and the neutron is neutral, as the name suggests. So neutrons, neutral, protons, positive, electrons, negative. Now, normally speaking, in a balanced state with no forces applied or anything else going on, our atom will be in a neutral state overall, because the number of protons will equal the number of electrons. That means we have all of our pluses equal all of our minuses. So we are in a neutral state, no overall electrical charge. Okay, so how do we get electricity to flow? Well, next thing we're going to look at is our copper atom. So copper, which we all know makes wires, it's a good conductor. Chemical symbol Cu. It's made up of, again, our nucleus. So let's draw the nucleus in the middle with a number of protons within that nucleus. Okay, we've also got a bunch of neutrons. I can't remember what colour I did neutrons. I'm going to pick pink. I think that's what they were. Okay, got a bunch of neutrons. and then orbiting them we have electrons. Now the number of electrons is quite important. Okay, so the electrons orbit in a number of shells, layers. First shell has just got 2 electrons. The next shell, layer or orbit or cloud, lots of different words used to describe, has got 8 electrons within. And then our final one has got 18. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. It's the best I've done so far. Okay, so the next shell, sorry, this is not the outer one, but the next shell has got 18. And then we've got one further shell, which has got 1 electron orbiting all on its own. So let's have a look at the number of subatomic particles within our copper atom. Protons. Okay, we have 29 protons. Neutrons, now this is not particularly important for anything because, as I say, they do not have any electrical charge. So for us as electricians it's not important. For physicists and metallurgists it's important. I'm pretty certain we've got 35 neutrons, or it could be 34. Now sometimes the number of neutrons does not equal the number of protons. That's because there are different isotopes of lots of materials or lots of atoms where they may have more or less neutrons. Some are stable, some are not. I'm pretty certain, if I'm right on the number there, 35, that this is a stable isotope of copper and it won't decay like radioactive materials do. Okay, and electrons. So we said we had 2 in the middle, we had 8 on the next row, 18 on the next, 1 on the final one, and that comes together to give us a total of 29 electrons. So yeah, you don't have to be a great mathematician to see that in this case our protons equal electrons, and therefore we have a net 0 charge. Okay, there is no charge on this copper atom. So how do we get electricity to flow? Well, that comes with the structure of copper as a material. So let us have a look at a conductor, a length of copper wire. So this is a very unusual piece of copper wire. Don't often get a piece of copper wire which is 1 atom thick, and that's what I'm going to draw here. So there is our copper wire, 1 atom thick, just basically a row of atoms all lined up together. Let's add some more in there. Okay, so within this piece of copper wire we've got our atoms, and those atoms all have this single electron on the outside. Now I'm just going to pop a little electron next to each atom. It's in a little blue dot there, and they're kind of, because they're on their own on an orbit, they're quite loosely held in place, and that means that they are liable to be dislodged by forces. We can actually cause those electrons to move throughout the material. In fact, as it stands, the electrons kind of drift around. They kind of move around the material, no particular direction because there's no particular force in them. Like a crowd, you might think about a crowd at a concert or a football match, and they're all just milling around. There's nothing particular going on. There's nothing to make them all go in one direction, like the bar opening or fire exit opening and a fire alarm going off, or band comes on stage and then there's a force, and or attractive or repulsive force, and people will move. I'm just going to go back to the previous slide just because I want to talk about the forces within an atom. Now remember, we said that our protons have a positive charge and our electrons have a negative charge. Well, I don't know if you remember magnets, where you have a north and you have a south pole on a magnet. So with that magnet, if we was to place another magnet nearby, if that magnet had a south pole at this end and a north pole at the other end, oops, I don't want to do that, I want to do the north pole in red, we would have a repulsive force between those two magnets. Okay, there will be a force pushing them apart. You try and push together, south and south or north and north, you get repulsion. Okay. Now, if it was the opposite, if we had a north and a south facing each other, we would get attraction. So if I draw another magnet here, and we put our north pole there, and a south pole there, between those two magnets, we're going to get a force of attraction. Okay, so that's going to be attracted to that way, that's going to be attracted to that way, the two magnets are going to be drawn together. Same happens with electrical charges. So we have a rule which is that like charges repel and opposite charges attract. Okay. So just like the poles on a magnet, same thing happens with electrical charges within the atom. So the electrons having a negative charge are attracted towards the nucleus. They're all being pulled in towards the nucleus. They're also repelled from each other, so they're trying to push away from each other. So you kind of get a balance where they will kind of sit where they sit and they will be stable. Apart from this one on the outside, it's a long way from the middle, so the charge, the attraction there is quite small, and it's also got lots of other electrons around, so they're all pushing it away, which means it's quite easy for that to be dislodged by a force. Okay, let's go back to here, and let's imagine we apply a force. In this case, we're going to connect our copper wire to a battery. So our battery has got one pole which is positive, okay, and one pole which is negative. Now remember those charges on those electrons? The electrons have a negative charge. Likes repel, opposites attract. So those electrons are going to be pushed away from the negative charge on that end of the battery, and they're going to be attracted towards the positive charge on the other end of the battery. In fact, the battery itself is actually filled up with excess electrons at this end, and at the other end we're going to have a whole bunch of atoms which are missing electrons, so they therefore have positive charges, and nature likes to balance things out. So the electrons are going to flow away from the excess end through the conductor down to the other end where we've got missing electrons, just to try and level things out, almost like water trying to find a level. So essentially that's what electrical current is. We connect a conductor into a circuit, we apply a charge at either end of the circuit, and the current, the electrons, will flow through that circuit. You might be thinking, hang on, what's going on here? Current's flowing from negative to positive. Electrons flow from negative to positive, but conventional current, so this is the current we talk about when we are doing circuit design, whatever, is the opposite. Conventional current always flow from positive to negative. It's really down to an accident in the initial kind of discoveries and experiments around electricity. There's two ways it could be, and someone got it wrong. But that's an introduction to electron theory and the atomic structure.